Hey guys, welcome back. Today we're working on the exam review for the upcoming first exam, dynamics. This problem is centered on angular momentum, and we're talking about a change in orbit. So let's get to it. So we're given that we're talking about an orbital shift, and there's a satellite orbiting. This is the Earth, this blue ball here. There's a satellite orbiting at 185 miles from the surface. It's orbiting the Earth, and at point A, there is a burn that sends the satellite along this trajectory, and another burn at point B that results in an increase in speed of 4910 feet per second, and then it's in orbit. So we are asked to find the speed of the satellite as it approaches B, and the increase in speed resulting from the firing at A. And also, sorry, I forgot to mention this, the orbits are circular, which allows us to treat this like a normal or it's a semi-normal angular momentum problem. So I went ahead and did some conversions, made a table. So we're given the distance from the surface. We're going to need, for our equations, which you already know, we're going to need the radii, and we're given velocity in feet. So what I did was I added the height for each of these positions to the radius of the Earth, which is 3960 miles. I converted it to feet, and these are those values. So we'll be using feet in our equations. First things first, we need velocities, right? We're going to need the velocities at A and B, because when we think about what is happening here physically, we're going around at VA, right? So in, I guess, our first phase, let me see if I can get my pen to work here. Hopefully it will. It was cooperating earlier. I really like this one, so I'm hoping that I can make it work. Let's try here. So we're going VA. So then we, at 1, then we're going VA plus some sort of a delta VA, and we can call this the transfer speed. All right, so then we're going to transfer speed through here, then this is, I guess, 2, and then we have another burn. I guess maybe these aren't arrows. These would be, or excuse me, they're not plus signs, they're arrows, right? And then at point B, then we get VT, and then we get plus this delta VB. And this right here is VB, right? This is our orbital speed. So they share this VT, but what we need to know right off the bat is what the heck is the orbital speeds? So let's derive a general equation based on what we've got so far. So we'll say A, and we want V. So sum of the forces, Newton's law, sum of the forces equals mass times acceleration. All right, so the sum of the forces for the satellite is limited to gravity. We can use the big gravity equation, and we'll say G M. So G is the gravitational constant, as you know. Big M is the mass of the Earth. Little m is the mass of the satellite. R squared is the square of the distance from the center to the satellite, and that is equal to M. And the acceleration is the normal acceleration, so that is v squared over rho, v squared. Rho is the radius of curvature, so the radius, so r, and m and r cancel this side. So we're left with v squared equals big G, big M over R. We don't have G or M, but we do have big R. So we can use this substitution, and we'll just substitute G R squared in for GM. So that gives us G R squared over little r. And when we solve this for V, then we get V equals the, we'll bring R out, right? R times G over little r. So it looks super compact. And in fact, it is. Well, that's awesome. And we have these values, right? So this is a constant that is here. G is 32.2, and R are these values. So I ran this through my calculator. I'm not going to make it wait, but what I came up with was that VA equals 10078 feet per second, and VB, wait, I have it backwards. VB was that VA has to be faster. So 25,361.7, so let's just go 362 feet per second. Okay, so these are the orbital speeds, right? So when the satellite is orbiting at A, it is going this fast, really fast. What is that? That is 5 miles per second. Out here, it's roughly 2 miles per second. Awesome. Okay, so what do we want here? We want the speed of the satellite as it approaches B. So how does that work? Well, that's where we started. So we could say V equals VT plus delta V, right? And here we're interested in VT, right? The speed as it increases. By the way, I need to back up a second. The VT here and VT here are not the same. I spoke in error. It is slowing down, right? Because it is affected by gravity. So typo, apologies. All right, and we are interested again in VT, and we'll say VT at B. All right, so just rearranging the equation, with VT at B is equal to V minus delta V. And we have those values. So it is 10, 0, 2 zeros, 78 feet per second minus 4910. So, and that I guess is also feet per second. So V JB equals 10078 minus 4910, 5168. 5168 feet per second. All right, cool. Sweet. So now we are looking for, just checking to make sure that is matching up with my notes. It does. See, 10078 minus 4910, 5168. Yep, okay. We're good there. Now we have to take a slightly different approach for B. Okay, with B, what we know is that the increase in speed. So if we think about the transfer, then we have the angular momentum is conserved. So we're able to use the conservation of angular momentum equation, which, as you know, is this guy here. So let's do it. So we say RA MVA equals RB MVB. And here we're talking about the transfer. So I'm just going to put a T there and a T there. And the radii are going to be specific to the endpoints, right? So RA is here, RB is here specifically, and can cancel those. What are we interested in? We're interested in the speed. So we have VBT, we need VAT. So if we just rearrange the equation, then VAT equals, it's like a moment equation, right? RB, and actually angular momentum is intrinsically related to moment, right? Rotation. A and VBT, right? So we know the transfer speed. The transfer speed is 5168. So this is equal to that, and that. I'm just going to plug this into my calculator. Well, let's see. So the velocity is, did I reverse those? Okay, I did reverse those. So it's going to be B over A. All right. So let's see, alpha. In my calculator, what I did was I stored the values so that they would be easy to access. That's going to be times 5168. And I get a transfer speed of 32,728. So it lost a lot of speed. Okay, so this gives us the transfer speed, but we're not interested in the transfer speed. We're interested in the increase, right? So the increase is going to be the difference between these two, right? So again, here we're leaving, so we can say that the transfer speed, VAT, is equal to VA plus delta VA. And we're interested in delta VA, so by extension, delta VA is equal to the difference between these two, so VAT minus VA, and that is what that is, 32,728 minus 25,362, and 32,728 minus 25,362 is 7366. Okay, so this, and sorry, this is delta VA. So let's do this. Delta VA equals, it's a little bit messy there, but you get the idea. All right, so that is how we tackle a change of orbit problem that requires us to consider angular momentum. And that's it. I wish you guys luck on the exam. I am sure that you will crush it.